Today we'll be talking about REAL Space Navigator version 2. That's basically what we've made in the last months. And if you are aware about the version number 1, you probably see that this version has much more molecules, like 6 times more molecules than the previous one. Franca?
Yeah. This is a joint project between BioSolveIT and Enamine, as you know already. And we at BioSolveIT are located here in Germany, and we're a rather smallish company with about 20 software developers. And we put our basic effort in development of fast, visual, and easy-to-use software, which is not only for expert modelers, but for every chemist as well. And our software targeted structure-based, ligand-based, as well as fragment-based lead discovery. We're not only developing software, but we're only offering modeling services as well. So if you have problems with any task which we can advise with, please feel free to contact us.
Okay, for Enamine is a Europe company. It's located in Kiev, Ukraine, and it's a chemical company that provides compounds and services, including FTE. It has more than 600 chemists, 10 its own buildings. Current stock contains more than 2.5 million compounds, including building block and screening compounds. And Enamine has biology services that can do HTS, ADME, and studies in animals. Anka?
I would like to start with the motivation of this project. And we were looking for a way to explore the chemical space more than it's just the typical 5 million molecules that you can buy on eMolecules. And the question is separated in 2 parts, namely, how can I build such a huge space, which is Euro's part of the talk, and how can you find anything in such a huge chemical space, which is our part. And imagine you could just jump from anything you know to something which is distant yet alike. So, which means similar in a chemical way, but namely different in its chemical structure. And we try to do so to get interesting results, which are hopefully as active as the seed compound you have started with, but completely different in its chemical scaffold, but readily available from a vendor catalog on the other hand side. Yuri?
Yeah, thank you, Veronica. Okay, if we're talking about chemical space, we probably think about the building blocks and the reactions to combine them. If we're talking about Enamine's chemical space, we have about 145,000 building blocks that can be combined via 200 parallel chemistry reaction procedures. And this will really gives you billions of molecules, and that's basically Enamine universe. But in reality, not all the molecules from that universe can be accessed synthetically. And the portion of the space, we call it real space. Real is an abbreviation for readily accessible. Contains molecules that can be indeed accessed synthetically within 3 weeks, and the synthesis success rate is over 80%. Okay, yeah. So so far we have 2 ways to explore this real space. One is our real database. Current release of real database is 680 million molecules, and it contains enumerated molecules. It's a classical database. Another way to explore this space is actually the Navigator, the joint product of Enamine and BioSolveIT. And just a few words about this real space, why we actually separated from all the Enamine virtual or Enamine universe. So real space is based on validated chemistry. That's why the compounds in the space can be accessed. We include in this real space only high-score synthetic procedures that are developed here at Enamine in the lab. And these procedures have high success rate and are validated in number of experiments. For example, for this top procedure, you can see that this oxidizole formation occurred in more than 8,700 reactions, and the success rate and average yield for this synthesis is pretty high. So this simple reaction allows us to generate a space of almost 3 million molecules. In real space, we do not include the low score procedures or the procedures that are under development. For example, the direction below, you can see that it's still ongoing. It's only 30, like 50 experiments have already been set, and the success rate and the yield is not that great to include it in the real space. Franca? So we also validate the reagents. So only qualified reagents are included in this real space. The same situation. So you see the high score, we have the high score building blocks where all the statistics is pretty good. The success rate is high, are included in this real space, while the building blocks with poor statistics, they are excluded from the real space. And if I'm talking about statistics, I mean that the statistics collected from our reactions, from the reaction set here at Enamine. You can have different statistics for the building blocks, but what we aim to deliver the compounds here with Enamine capabilities. Next. Okay, so Real Space version number 2, or Real Space Navigator version number 2, has much more reactions included. Now we have 139 high score validated reaction procedures, now 1 to 3 steps, and 2 to 3 reagents. We also included more building blocks. Now we have 58.7 thousand high score building blocks. And the number of procedures and number of building blocks allowed us to actually increase the space, as I mentioned before, like 6 times. Now it's actually almost 3.8 billion feasible molecules. Franca?
No, this is you.
Okay, so that's the major changes. So we have 20 more validated reaction procedures added, 4.9 thousand reagents, and now we are including tri-component multi-step reactions, like the one that is drawn here for the triazole formation. Franca? Yeah. So Real Space Navigator versus Real Database. As I mentioned before, Real Database is a conventional database with the SMILES, enumerated molecules, while Real Space Navigator doesn't have any molecules, but rather syntones and reactions, how to combine them. And the molecules are actually generated as similars to the query molecule. The size, yeah, the Real Database is 680 million structures, while a Real Space Navigator has approximately 3.8 feasible structures. Real Database is actually filtered. It's more in the drug-like space, while Real Space Navigator is not limited. You can find the molecules as large as 1,000 Daltons there. As for the reaction protocols, Real Database has more reaction protocols, and it includes not only high-score reaction protocols, but the low-score ones as well. The same with building blocks. We have more building blocks included for Real Database than Real Space Navigator, and that's because we have some low-score building blocks included. Both databases are based only on in-stock building blocks that are over 10 grams in stock. That means that, for example, if you come to us in a few months and order compounds on the building block, you still can be sure that we're able to synthesize the compounds because we have the building blocks in stock. As for the compounds that included in both Real Database and Real Space Navigator, we have the building blocks combinations high score for the navigator, and high score and low score and high score for the real database. Next. Okay, that's just the diagram to show you where we have. So we have approximately 92,000 building blocks, over 10 grams in stock, but not all of them have been validated in our reaction procedures. So some of the fraction is not actually included in this real space, and the 70,000 building blocks are in that 92,000, and also 58,000 building blocks are overlapped with the building blocks from real database. So that's Real Space Navigator is built on the small fraction of the building blocks, but those fractions are overlapped. The same with reactions. So as I mentioned before, in Real Space Navigator, now we included only high score procedures. That means that some of the fraction we have here, 161 reaction procedures that are that built a real database, they have a medium score, and they're not included in Real Space Navigator yet. Next. Okay, and because we have so many reaction procedures to validate more and to include, we're expecting even further growth of the navigator, and maybe in version number 3 we have 5-10 billion molecules to present to you. And it's possible, Franca? It's possible because we have around 200 reaction procedures, and as I mentioned, 92,000 building blocks in substantial quantities in stock. Yeah. Maybe trillions will be accessible soon.
Okay. Yeah. So coming back to the algorithm that goes under the hood, it's called Ftrees because you have built the space as the one part, and you have to search it as the second part. So the way to search the space is by applying a similarity algorithm. It's called Ftrees, and Ftrees is a pharmacophoric kind of descriptor of a molecule. Let's, for example, take this query here. It's a molecule from the PDB, and Ftrees builds a tree. So there are branches, but there are not cycles, only trees, of this molecule regarding the pharmacophoric properties of the individual parts of the molecule. So let's say, for example, this heterocycle here is of the distinct volume, it's a number of rings inside, and it has some features regarding donor and acceptor, and there is some aromatic feature inside. And just like this, the algorithm builds up a tree for any of the molecules, or let's say parts of the any of the atoms or parts of the molecule. And this one is searched inside the space and compared to the molecules that are inside. If I overlay them, no, I'm going in the wrong direction, sorry. Maybe it gets clearer when I overlay them. So each of those nodes belongs to a special part of the molecule, and the same is done for the virtual hits, and if you compare them, you get a similarity value. And you can get out those colored pictures as well to make you understand why the computer sees two molecules as similar, while the chemical eye sees, of course, differences in them. Let's say here, for example, the aromatic ring on this side and containing heteroatoms, while this is superposed to a vancile ring on the other side of the hit molecule. And this will help you to understand why these two molecules are similar. And if you have those mapping algorithm already, it can help you to do 3D alignments of the molecules as well if you are coming from the ligand-based design side. The strength of this descriptor is to find scaffold hops. As you saw maybe before, it's a bit fuzzy of the parts of the molecule. So it's finding a 6-membered ring similar to a 5-membered or 6-membered or 7-membered ring, a heteroaromatic ring to a just carbon-containing ring. And with that, you can do very good scaffold hoppings, like, for example, in this picture here. This is a very old publication from 1998, where D4 agonist was searched in the World Drug Index. And you see here, these are the number of the data. This is the percent of the database. So on the top 2% of the database, a lot of known other agonists were found. So every of this dark line indicates that there is another known agonist inside. So you see there is a real enrichment in the top 1% of the database. And you see these molecules here are other agonists, and they show some really good differences in the scaffold to the query. So with Ftrees, you can not only search for very close analogs, but for scaffold hops too. And with the current space, we of course wanted to find out, do we find drug-like molecules? And to do such a benchmark, we went to the FDA approved drugs and filtered them to those that are Rule of 5 compliant, to leave out the very small ones like just magnesium, or the very big ones like the steroids. And took 709 of those molecules and searched them in the real space. And you see here, these are the numbers that we have found. So overall, these are 709 molecules. And if you see the statistics here, you can see that 100% are found with a similarity above 0.8. So which means for the most of the molecules, a very, very similar molecule is found in the real space. For 60, so let's say 10% of the molecules, a close analog, so the same molecule with a similarity of 1, is found back in the space. Good thing to know as well is that all queries could be processed, so there was not a problem with one molecule, and it went very, very fast. So every query took about 1 minute on a standard PC. And the median similarity of this is 0.696, sorry. So for every drug-like molecule, a very close analog can be found in the real space. And as Yuri mentioned before, there are two versions, the REAL Space Navigator, which is using the Ftrees algorithm, and the REAL Database, which is using the MADFAST algorithm from Chimaxon. And just to point out the differences here, as I said before, Ftrees uses this topological pharmacophore descriptors. So it's not a fingerprint query where you go from one atom to the next one and compare, is it similar, yes or no. So this points out to the strengths of the individual algorithm. So the MADFAST algorithm on the real to search the real database is very good for find very, very close analogs, while the Ftrees is a bit fuzzier. So it can, for example, not perfectly discriminate between ortho, meta, and para substitution of a ring, but it helps you very good to find scaffold hops. And the same thing is, it works for chemical spaces, which means it's reagents and like a Lego set rules how to combine them. And this allows us to go up to way, way bigger spaces, up to the size of 10 to the power of 20. While the real database is fully enumerated, which means there's one molecule written down after the next, which is possible to search with conventional algorithms like these fingerprint algorithms just to, let's say, about billions. So it's quite limited. It's still way bigger than what you can buy at the moment, but from conventional catalogs. But it's limited to the speed of the graphical process unit on your PC. So another point to state here is, the real database is available via a web page, which is quite good for some people, but you have to submit your query to the internet, which is sometimes difficult regarding your IP. But the Real Space Navigator is a tool that you can download, which runs on your local PC, so completely behind your firewall, and it needs only 4 GB memory from your PC, so you can still continue working. How can you now access the real space? So if we had a majority of computational chemists here, so they might be fans of Pipeline Pilot, for example, where you can just download our nodes and tell the searching node where you have put the space and submit your query there and get the results done. Same is available in KNIME. You just draw your query and search it with the Ftrees FS search node and get the results. But for those who are not expert computational chemists and don't like data mining tools so much, we have developed the Real Space Navigator, which is a hopefully quite simple to use interface. And as I said before, it's a small tool that you install on your PC, so it's running behind your firewall just on your local machine. So the Real Space Navigator is a tool that you install, click on the icon, and then it opens up. And you see it's a quite minimalistic interface here. You have a query side, and later on the results will fill up on this side here. And you can submit your query on 3 different ways there by just loading it from any file that you have already, for example, your PDB file or just a mol file, whatever you have. You can drag and drop your molecule here, or you can copy paste it from your favorite drawer. Just to make clear for here, there are a lot of molecule formats that you can use, and we support the standard ones like SMILES, MOL2, and SDF. So when you just use your Marvin to draw, for example, then don't just do Control C, Control K, but Control C, Control V, but you have to push Control K and copy as other SMILES for here. Okay, now that you have imported your query, you have one option to change. That's a slider here on top, where you can decide if you want to search very close analogues or more go to the other side to find scaffold hops. Let's say you come out of a big virtual screening where you have screened Enamine libraries and want to find close analogues, then you go for the more similar side. But if you have found a hit that's already patented and want to discover similar but different molecules, then you go for the more surprise side and hit the go button. And then it will search the real space, and it will take between 1 and 3 minutes regarding the size of your query and your computer. And then automatically the results side here will fill up with the molecules that were found in the real space and the similarity value behind. And you see here are check boxes, so all of them are already pre-checked, that you can simply export the list, but you can make your choices here individually, uncheck those that you don't like, and hit the save button. And then you get an SD file that you can send to libraries at enamine.net to get a quote for the molecules that you want to order.
Okay, yeah, as I mentioned before, so this real space is designed to be delivered by parallel chemistry that is good for library synthesis. And you can get compounds there as fast as 3 weeks. I mean, this to be synthesized in 3 weeks. And the success rate for the real space, we expect over 80%. You don't need to select the libraries. You can do the cherry picking. Enamine supports exclusive supply. And for all the real compounds from Real Space Navigator or from Real Database, there is a fixed price. It depends on the number of compounds and amount ordered. For more information, yeah, you can contact Enamine. For this, I would like to thank you for your attention and go and grab a copy of Real Space Navigator and enjoy using it. Thank you.
Yeah, thank you, Yuri, for this interesting talk, and to our attendees. And before you leave, I would like to ask you one last poll. Namely, now that you have seen the Real Space Navigator 2, we are wondering, what would you wish for next? Would you wish for even bigger spaces, let's say up to more billions, but take the problem that the delivery rate might drop a bit? Or would you be happy if we combine the space with your in-house building blocks? Or like an automated process when you give a PDB to find different analogues that already well dock, so you don't have to do work of post-processing the results from the space? Or would you want to include other ways to search the real space, like for more substructures that you know already that are important to be found? Or would you be happy to have a web interface for the searches? So half of you have already voted. I would be happy if some more of you made their clicks. Thank you very much. And I'm going to close this poll in 5, 4, 3, 2, 1. Okay, I close it. And to share the results with you, there's a majority of 2 points, which is an automated workflow of finding different molecules to a given PDB structure, and other ways to search the real space with substructures. Okay, thank you very much. With this, I would like to close for today, but let you know at the last point where you get the Real Space Navigator from. It's www.biosolveIT.de/Real Space Navigator. You can grab a copy there for free and try it out. If you want a license, please contact us. There's a button in the tool that helps you to do so. And with that, I just wanted to feed in one more question that was put to Yuri. Yuri, the question was, what is the threshold for a high-score building block, and what's the threshold for a low-score building block, and what's the procedure to select them?
Yeah, thank you, Franca. The procedure to select them is based on experimental data. We basically test each building block that is delivered from our chemist, and it's in substantial quantity to be tested in this parallel chemistry procedure. Imagine we have a new amine, and we would like to see whether it's a high score or low score. So basically, we take it and test it in 20 common reactions, let's say acylation, some reductive amination, etc. And if we, for example, see that the success score for this building block is low, let's say less than 70%, we either test it with the building block in different reaction procedures, because for reduction amination reaction we have at least 4 of them established. Or if we see that this building block is not good, we just excluded it from the enumeration, or actually not included in enumeration. If we see that the score for this building block is high, so basically a lot of experiments have already succeeded with this building block, we expanded it to more experiments, and if we see that everything is okay, we included it in the enumeration.
Okay.
Anka?
Thanks, Yuri. Is anybody else having a last question? Then please type it in now, because otherwise we can close for today. No, I don't see any questions coming in. So thank you everybody for coming, and please try it out. And we are happy to get your comments on how you like this, and what do you see for improvements or what's missing for you. And we'll be happy to be in contact with you. So thanks everybody, and goodbye.
Thank you. Bye.